Hi everyone, my name is Mahdi Belbasi. I'm a PhD student at Pennsylvania State University. Today I'm going to present my work with Martin Fürer called An Improvement of Reads Through Its Approximation. Uh, so let's get started with the outline. So first I'm going to talk about the definition and also Reed's algorithm because we need to know the details of the algorithm, and some of the details are missing in this paper. So we are going to fill in those blanks and also give a precise time analysis. And then we are going to describe our improvements and talk about our algorithm and then analyze its running time. So let's start with tree decomposition. If you're given a graph G, a tree decomposition is basically a tree such that each node in X is associated with a bag of vertices of G, such that these properties hold. The union of all bags is basically all vertices of G. So every vertex should be in at least one bag. Every edge, for every edge in the graph, we must have one node that has both endpoints in it. And if you look at only one vertex of the graph, so the nodes having that vertex form a subtree. They are connected. So that's tree decomposition. It is what is tree width. Basically, we say the width of a tree decomposition. It's the size of its largest bag minus one. The reason that we have that minus one is that we wanted to have width one for trees, right? So the tree width of a graph is the minimum width among all possible tree decompositions. And then we have that tree width of any tree is one, as I said. And then in this paper, but we are not going to subtract that one there because we are going to be consistent with the Reed's algorithm, and he Reed's paper, and he doesn't subtract one. So, but why tree width is important? We know that many NP-complete graph problems can be solved relatively fast if they have bounded tree width. In fact, there is Courcell's method theorem saying that any graph property which can be described in a monadic second order logic of graphs can be decided in linear time for graphs with bounded tree width. So it is vital to know what's the tree width. And once we know the tree width, we also need to know what is the tree decomposition. We have to have one good tree decomposition to apply dynamic programming on that. So, but before that, let's see what is FPT. A fixed parameter tractable algorithm is an algorithm which runs in O of fk polynomial of n, where n is the size of the input, k is the parameter, and f is a computable function. Many NP-complete problems obtain FPT algorithms where the parameter is tree width. So it is important to have the tree width to know what's the bound of tree width. And also we need to have the tree decomposition because most of them use dynamic programming and we want to solve these problems. So we must have access to the tree decomposition. So here we are going to present one of the algorithms, which is we start with Reed's algorithm. But before that, let's look at the difficulty of this problem itself. So we said that if we have tree decomposition and the tree width is small, in fact, we can solve many of NP-complete problems very fast. But finding tree decomposition itself and the tree is deciding the tree width itself is NP-complete. That's what Arnberg et al. Showed in '87. So we also need to find that tree decomposition, but it is difficult to find that it is NP-complete, but we can find, we can approximate that. So now let's start with history. This is a table that I have some of the works that have been done in this area. So it started with Robertson Seymour's paper, and they gave n square algorithm. This column shows the dependence on n, this column shows the dependence on k, and here we have the approximation ratio alpha and then comments. So I'm gonna focus on algorithms that run faster than n log n or faster. We said logagran improved it to n log square of n. Oh, by the way, we're only focusing on constant factor approximations, right? So logagran gave n log square of n. And then Reed was the first person who gave n log n algorithm. So he was focusing on improving the dependence on n, so he doesn't focus on dependence on k that much. So we have n log n here, and then we have 2 to the power of 24k k factorial, which is very huge number. Later, both Lander et al. Had one algorithm which runs in n log n, but they also have another algorithm which runs in n. So this is, from theoretical point of view, this is the best possible algorithm, and it also runs in 2 to the power of k. But the problem is they don't mention the dependence on k in the exponent, and we believe it's very huge, and also they use a very sophisticated data structure. So we thought maybe it's good to sacrifice on dependence on n and add one, tolerate that addition of log of n here, but instead we gain a lot in the exponent, and then we actually can make this applicable in few applications if the k is very small. So that's what we are going to present in this paper. It's a 5 approximation. To the running time is 2 to the power of 8.766 k square n log n, and this is good because it has a small coefficient of k in the exponent. So now let's start with Reed's algorithm. We said that Reed, we are going to first explain Reed's algorithm. Reed starts with a balanced separator of size at most k that separates the set of vertices V into two parts, V1 and V2, and we solve this for graphs V1 union S, the graphs induced on that set, and the graph induced on V2 is union with S independently. We find 3D compositions for these two, and then finally we merge them to find the 3D composition for the entire original graph. So let's start with the weakly balanced separation of W, if W is a subset of vertices. This is a triple X, S, and Y, where X and Y are subsets of W. And so basically, S is going to separate X and Y, W, such that, and these are all disjoint sets, right? W is either X union Y union the part that intersects with W, the part of S that intersects with W. As I said, S separates X from Y, and size of X and Y, their sizes is between 0 and 2/3 of the size of W. So the figure that we are going to show in the next page actually will make it more clear. So if this is G, we have W, we have G minus W. So S actually separates W into X, S union, S intersection W, and also W itself. And as you see, X, size of X and Y together is not greater than 2/3 of size of W. So it splits W in a somewhat balanced way, but it doesn't say anything about the rest of the graph. So it might separate in a balanced way as we have here, or in a very biased way. Maybe this is empty, or maybe just one vertex, two vertices, or whatsoever, right? So this is a weakly balanced separation of W. So we separate W at most the 2/3, right? At most 1/3 to 2/3. So this is how Reed proceeds. Reed finds representatives. What is a representative? He runs, basically, instead of checking for every vertex, he groups them, picks one representative from each group, and then tries to separate those, and then hoping that their corresponding groups will go to the same side, right? Instead of looking at every node, he just picks one representative. What's the threshold for representative? Each representative should represent at least n over 24k vertices. So he does a DFS. Let's let V be the deepest vertex in the DFS tree, such that it has size, its subtree has size at least n over 24k, which means it represents at least those many vertices. calls it a representative, and its weight is the number of vertices that it represents, which is the size of its subtree. So, and let W be the set of all representatives. And now we are going to give a weakly balanced separation of W, right? So finding balanced separators for the entire V is costly. So instead, Reed focuses on separating separate representatives most of the time. So there is one thing here. We separate representatives, hoping that the entire graph is separated in a good way. But how can we be sure? So it's actually, let's look at the bad incident. What is a bad incident? We put one representative, let's say, into the left part, and some of its subtree goes into the right side, right? In order to have this incident happen, we must have one vertex in a separator, because this is a connected path, right? It goes from the root to some vertex in its subtree. So it must go through the separator, which means it requires one vertex in the separator. However, we have the upper bound on the capacity of the separator, which is k. So not more than k such incidents can happen. And in each of those incidents, we actually have n over 24k vertices. So at most, n over 24 vertices can go to the wrong side, the side that the representative is not sent to. So the error rate is actually 1 over 24. In Reed's algorithm, we start with 3 decompositions that differ. The adjacent bags differ in at most one vertex, and we call such 3 decomposition good 3 decompositions. And it's easy to convert any 3 decomposition to a good 3 decomposition in linear time. So then we have a strong centroid definition. Basically, that's a strong centroid of a good 3 decomposition of a graph G with respect to W is a node X of the 3 decomposition that none of the, if we delete that bag from the graph, none of the connected components have more than 1/2 of W minus B of X vertices of W, right? So, and we know that it exists, and you can see the proof in our paper, so we don't have time to go over the proof. So Reed says, consider the optimal 3 decomposition. We don't know what it is, but it exists. So we hope to find it, but we are not able to find it. Instead, we find something which is 1 over 20, in terms of weight, is 1 over 24 n to the left. Without loss of generality, assume it's to the left. And then once we have that, it is in terms of weights of representatives. Once we want to go back to the actual volume, actual size, we pay the error once more. So in the end, we have left side, right side, and the separator, call it LSR. So we have size of L and R. We started with weights 2/3, 1/3, and we paid error rate twice, and here twice, right? So finally, L and R have size between actual volume between 3/4 and 1/4. Now we see why Reed picked 24, because he wanted to look for something 2/3, 1/3, but then he wasn't able to find it. So he went all the way up to the simplest rational number close to this, which is 3/4. So if you subtract these and divide it by 2, it gives us 1 over 24. So how to find these separators? So in the beginning, Reed checks the possibility that at least one vertex goes into the separator. Then, so he first looks at the possibility going into separator and not going to the separator. Once he handles that, and then now everything, nothing is going to go into the separator, only then he decides every vertex going left or right. Right? And if something goes into the separator in the beginning, he places it there and removes that from the graph and does a new DFS from scratch, which is costly and might form a new set of representatives. And once that happens, then he has to go check for 24k. He has at most 24k representatives, and each of them might go left or right. So it's 2 to the power of 24k possibilities to be checked. And then Reed mentions that his algorithm runs in n log n for fixed k. So it means he doesn't look at the dependence on k. But our analysis shows that actually its running time is greater than 2 to the power of 24k, k factorial m minus k, which is 2 to the power of omega k log kn. So it is very 2 to the power of 24k is way greater than k factorial for a small k. So that's a bit misleading. So Reed claims that also his approximation ratio is 5. The approximation ratio of his algorithm is 5, but we show that if you have to do splits by actual volume every log k splits, which is the costly one. You do log k splits by weight and then one split by volume, and then you get 5. Otherwise, you get 7. So our improvements, we have 3 main improvements. The first one is relaxed error rate. Instead of 24 and going to 3/4, we are willing to go all the way to 1 minus epsilon. So let n over c epsilon k, c epsilon be the constant factor that we have there. So Reed separates the case that V goes into the separator, not in the separator, but we go in a serial way. We pick one representative, check if it goes left, separator, or right? So, and only then we go to the next separator. And then if something goes to the separator, we place it in the separator, remove it from the graph, undo the DFS for its subtree, and then continue DFS to discover all vertices there, right? So we don't do DFS from scratch. This is the figure that we have. Let's say this is V, and then if we delete that X, Y, and Z, these subtrees will be without parents, but X can be discovered from here. Y can be discovered from something below that, right? We go there, we go to Q and then P. And then Z is not connected to something higher up. It's just only to our advantage because it gets disconnected. So Reed partitions into 2 parts. Also, the third improvement is that when Reed starts, he deletes the centroid. He says now form a 2 partition, right? So this is not that helpful because this partition after applying the error might be a bad partition. This is not good enough. We might be able to get actually better partition. So in the beginning, we let multi-partitions, and then we apply the weight, and only then we start forming 2 partitions, right? So this is C epsilon for Reed, and the C epsilon for us is we are willing to go all the way to 1 minus epsilon. But if we delete the centroid, no connected component has more than half the volume, right? So we are going to go from 1/2 all the way to 1 minus epsilon, and then we pay the error twice. So we get 4 over 1 minus 2 epsilon, which goes to 4 if epsilon is very small. So now let's look at the running time analysis. The time complexity of finding a balanced separator in terms of based on W is K prime, the current upper bound for the size of S, T prime, the current number of representatives, G prime, the current graph. This is the running time that we have. So, and here we don't send anything to this separator. It goes either left or right, that's 2. And then the representatives, we actually have 1 less. Here, it goes to the separator, and then the number of representatives decreases by this much. And these are the base cases, and Q is the constant factor showing up in the exact running time of the flow algorithm. So we have this, we solve that, and you see that C epsilon goes into the exponent. So that's very important to drop that from 24 all the way to 4 that we had, right? In fact, it's going to be 5 because we have this +1 here. And now we show that the time complexity of splitting based on V, the volume is this much. We go to one side at most epsilon of volume, at least epsilon of volume, the other one at most 1 minus epsilon, and then we add the separator itself, and we get this after solving. We know we do this only once, while we do the previous one, this one, every log k times. So if we put them together, This is the total running time plug C epsilon there, which was 4 over 1 minus 2 epsilon. We get this one, right? Now you see that the dependence on k in the exponent is shown by this. Says let's see 0 be log e log 5 plus 5, which is 8.765. For every c greater than this, a 5-hour approximation of the 3 bits can be computed in time 2 to the power of ck in log n. And this finishes our paper. This was the main result that we had, and we dropped 24 all the way to 8.765, and also we removed k factorial there. So thanks for listening, and I would be happy if you had any questions. Thanks.